So today in class, he was talking about Bernoulli random variables. Here's what I think you should take away from what he said in class today. So Bernoulli random variables. Basically, the idea here is you're talking about something where you have either a failure or a success. So an example could be flipping a coin, where you think of getting a head as a success and getting a tail as a failure, or whichever way you want to view it. Heads are not my favorite. Coins are not my favorite example because the probability of each thing is the same. So let's look at this example. Let's say we have an unfair coin. The probability of getting a head, which we're going to call a success, is going to be 2/3. And the probability of getting a tail, which we're going to call failure, that probability is going to be 1 minus 2/3, which is 1/3. We're taking it, and typically the thing that's the success we call P, or I should say, the probability of success is what we call P. This is our success. And the probability of what we call a failure is 1 minus P, also sometimes referred to as Q in stats class. If you take stats or have taken stats, you have probably seen this before, or will see it when you take it. And so then if I want to say, let's say we flip n equal to, I don't know, 10 coins. 10 is not the best choice here, but fine. And we ask the questions like, what is the expected value? Well, I should be a little more clear here, sorry. We're going to say that X is the number of successes. I always forget to do that. So in this case, the number of heads that come up when we flip n coins. So what is the expected value of X? What is E of X? And I know I watched the video, he did a ton of like manipulation of a summation and all this jazz. And at the end of the story, the answer is n times P, which is in this case is 10 times 2/3. So 20/3, which is how I would leave it, or if you want to think of it as a whole number with a little bit left over, 6 2/3. So if you flip 10 coins, all of them being unfair coins with a 2/3 probability of being a head and a 1/3 probability of being a tail, we would expect on average to get 6 2/3 heads. Now, obviously, you're never going to actually get that number when you flip one iteration of this, but if you keep doing it again and again and again and again and again, over time, you would expect the average to tend towards that number. And yes, there's a lot of math behind how you get from the expected value being this giant formula down to that, but I don't think you have to know that math.
What exactly would 20/3 signify here? Because I mean, I understand 2/3 is like it's a 2 out of 3.
Right. So what we're really saying, and if right, 20/3 is 6 2/3, right? So what we're really saying here, I flip 10 coins, and then on average, between 6 and 7 of them are going to come up heads. If I picked a number like 12 coins to flip instead of 10 coins to flip, then on average, you would have expected 2/3 of 12, which is 8 heads and 4 tails. And then similarly, the variance, which I will just point out because I think it's neat. The variance is the expected value of X squared minus the expected value of X squared, which is kind of cool. You don't actually need to know this, at least not for now. And that's going to end up equaling n times P times 1 minus P, which is nice. So in this case, that's going to be 10 times 2/3 times 1/3, which is going to be 20/9. And then the standard deviation is going to be sigma equal to the square root of the variance. I didn't actually write V of X over here. Sorry about that. V of X. That's just going to be the square root of 20/9, which simplifies to 2√5/3. I don't actually care about simplifying, but right, square root of 9 is 3, 20 is 4 times 5, square root of 20, square root of 4 is 2, so you get 2/5. So I think all you really need to know about this is how to calculate the variance and how to calculate the expected value. And how to read the question so you know what's what. Right here, my N is 10 because I'm doing 10 trials or 10 coin flips. My P is 2/3 because we said that was the probability of success. My Q is 1/3, or my 1 minus B is 1/3 because 1 minus 2/3 is 1/3. Questions about this? Yeah.
How's the unlucky there?
So I was trying to make up an example because I don't love the examples where the probability of success and the probability of failure are the same. Because in a normal coin, the probability of success is 1/2 and the probability of failure is also 1/2. So I'm just pretending like someone manufactured some coins that happen to have a 2/3 probability of flipping a head and a 1/3 probability of flipping a tail. It's not realistic, but it's just, yeah. A better example would be like a weighted die. Like you can't actually weight a die by putting literal weight in one side of the die, making it more likely that the side opposite of it comes up. So you can have a weighted die where say like the probability of a 6 was, I don't know, bigger than 1/6, maybe it was like 1, like sure. So no, I don't, let's not get too into that. You could do that, we don't need to do that. Other questions about this before we talk about, I guess, the polar coordinates for a second?
Wait, just
Mhm.
you just multiply the 2/3 and 1/3. Multiply that by 10.
Right. N times P times 1 minus P. That's your variance. Cool. All right, let's talk about polar coordinates for just a minute. So, and we'll look at a couple limits involved in this. So polar coordinates. Really, you can summarize polar coordinates with one picture, which might look similar to some trig unit circle kind of jazz. So this point here, I'm going to say that point is x comma y, because I have gone over x and up y. But you could also say that point is r comma theta, because you've gone an angle of theta counterclockwise from the x-axis, I should say from the positive x-axis, and you've got a distance of r from the origin to the point there. Two different systems of labeling any point in the xy plane. Right? You could label every point either as over up or angle out. And then if you know the Pythagorean theorem and some trig stuff, you can find all the equations you actually need to go from polar to rectangular or from rectangular to polar. When I say rectangular, I just mean xy. When I say polar, I mean r theta. So my equations are x squared plus y squared equals r squared. And then trig sine of theta is equal to opposite divided by hypotenuse. But we usually rewrite that as y equal to r times sine of theta. And similarly, cosine of theta is equal to adjacent over hypotenuse, but we rewrite that as x equal to r times cosine of theta. There is one other equation that sometimes comes up when you're doing this for real. I really would have a hard time imagining that's going to come up. But the other equation that sometimes gets used is the tangent of theta is equal to y divided by x, so that theta is equal to the inverse tangent or the arctangent of y divided by x. Again, this is really, I really highly doubt you'll see this if you're trying one of these limit problems, but I guess I should mention it. Yeah.
When that coordinates x, y, or
r theta,
is that insinuating that r equals x?
No, definitely not. So let me give you an example. So here's an example of two different ways of writing the same point in R2 in the two-dimensional space.
Is it like radians versus
Kind of, yeah. So we could say that x comma y is equal to the point, and I'm going to make up a point that I know is easy. Am I going to make it up? Let's see, can I? Sure. Let's say that xy is the point 2 comma 2 root 3. Hopefully that's good. Yeah, right? That should work. Okay. Equivalently, r theta, well, if I actually just draw this triangle here, if this side is 2 and this side is 2 root 3, then this length here I could find using the Pythagorean theorem. R squared is equal to x squared plus y squared. So r squared is equal to 4 plus 4 times 3 is 12. 4 plus 12 is 16. The square root of 16 is 4. So my R value is 4. And my angle here, I made up this one specifically so the angle would be nice. The angle here, I know that cosine of theta is equal to 2/4, which is 1/2. And I know that the angle when cosine is equal to 1/2 is 60 degrees or pi/3 radians. So these two coordinates, x, y, the rectangular coordinates 2, 2√3, or the or the polar coordinates 4, pi/3 represent the same point in 2 dimensions. It's just a different way of writing it. Now, do you have to be able to do this? Not really, no. But I'm trying to describe just kind of the difference between these two things. But yeah, we're definitely not saying the R is X and the theta is Y. Questions?
Can I get a repeat?
Yeah. So you can either, for this point I'm describing, sure. You can either go over 2 and up to √3. √3 is about 1.7. 2 times that is about 3.4. Ish. Okay. About right there. So I'm about like right there. So there's my over 2 and up to √3. Or you can say, I'm going to go an angle of pi/3. So my angle of pi/3 is like 60 degrees, about right there. There's my angle, pi/3, pi/3. And then you're going to go in that direction for a length of 4. And both of those things describe the same end point over there. Okay. So this is our framework. I don't think, again, if this is not the part that you actually need to know to be able to do the problem. What you need to know are the things I've boxed. The x squared plus y squared equals r squared, that y equals r sine theta, x equals r cosine theta. If you forget that, you can draw this little triangle and label the things x, y, r, and theta, and then derive them relatively quickly if you feel good about your trig. So then, how do we approach a problem like problem 1 from the practice exam? Well, literally, if they say use polar coordinates, you're going to take all the things and replace them with what they're equal to. So if I'm trying to deal with, say, the limit as x, y approaches 0, 0 of x cubed plus y cubed over x squared plus y squared, I'm going to take these 3 boxed equations and replace what I can with them. So here's what I would write. Yeah, there's one more important thing, and I did write this in the notes. I should point out, if x and y are both going to 0, 0, we're going towards the origin, right? So if we're going towards the origin, the radius, which is the distance from the origin, should be getting closer and closer to what? 0. The angle, on the other hand, doesn't really have any limitation. It could literally be any angle around, and as long as the radius is getting small, you're still getting closer and closer to the origin. What that means for us is if you do this and your answer still has like a theta in it at the end, it means limit probably doesn't exist because theta can be anything. So here we're going to rewrite this as the limit as r approaches 0. And then in the numerator, we're going to replace x with r cosine theta. We're going to replace y with r sine theta. And personally, if I see x squared plus y squared exactly, I'm just going to replace that with r squared. Yeah, you could say that x squared plus y squared is r squared times cosine squared theta plus r squared times sine squared theta, which is equal to r squared times cosine squared theta plus sine squared theta. And then you have to remember that cosine squared theta plus sine squared theta is equal to 1. I think you don't need to do this work. I think everyone's okay with you saying, yeah, we know x squared plus y squared is equal to r squared. So if you see exactly x squared plus y squared, just replace with r squared. Now we're going to try and cancel as much stuff as we can. So I'm going to write this as the limit. As r goes to 0. I've got r cubed that I can factor out. I'm left with a cosine cubed theta plus a sine cubed theta divided by r squared. I can cancel an r squared with an r squared. I'm left with the limit as r goes to 0, r times cosine cubed theta plus sine cubed theta. Whatever cosine cubed theta plus sine cubed theta is, it's some real number. But as r goes to 0, you're getting closer and closer to 0 times it doesn't matter. 0 times a real number is just going to be 0. And we're done. I feel like he did a little bit more work here. No, that seems sure. I don't feel like you need to write all that. Yeah, why are you using the squeeze there, dude? Yeah, I mean, I get doing extra work to try and show it because some people are like, how'd you get that? Like, okay, that's how we got it. But like, yeah, it seems.
Shows off that's where.
Yeah, that's really unnecessary.
Sometimes it has to have all that extra.
Yeah.
So
What he's saying at this stage is this here, the cosine cube plus sine cubed is for sure less than 2 and for sure bigger than -2 because cosine's always between -1 and 1 and sine's always between -1 and 1. If you add them together, it's definitely between -2 and 2. But yeah, I don't feel like you have to do that.
I'm kind of confused on the like side we have there, the x squared plus y squared equals, that whole thing. I don't really understand how that boils down to y squared.
So there is a trig identity that says cosine squared theta plus sine squared theta is equal to 1. And it comes from the fact that if you draw like a unit circle sort of deal here, and you say your angle is this, your radius is 1, there's x, there's y, cosine theta is equal to x over 1, sine theta is equal to y over 1, and then x squared plus y squared equals 1 squared, Pythagorean theorem, but then x is really cosine, so you really have cosine squared theta, y is really sine, so you have sine squared theta equal to 1. That's where that's coming from. I refer to that as the most famous trig identity because it's the one that comes up the most of all the trig identities you might have seen in your life. Let's look at one more example of this and then we'll move on. I had one here. Yeah, let's look at this one. This is problem 57 from section 9.1, in case you're curious. 9.1, number 57. I don't actually know if this converges or not, so we're just going to take a shot at it. I'm pretty sure it converges. Let's take a look. So the limit is x, comma y goes to 0, 0 of xy over the square root of x squared plus y squared. And to me, this looks like a prime candidate. Actually, I feel like we could do this one either way. We might actually talk about doing it either way. So, but let's do it using polar first. So all I'm going to do is I'm going to replace every x with r cosine theta, every y with r sine theta. But if I happen to see x squared plus y squared, I'm going to write r squared because it's easier. So we're going to rewrite this as the limit as r goes to 0 of r cosine theta for x, r sine theta for y, divided by the square root of r squared. This one, technically I should do that, yeah. So I'm going to rewrite this as the limit. So r goes to 0 of r squared sine theta cosine theta. No reason to put sine first, I just naturally do. I don't know why. And the square root of r squared is technically not just r, it's the absolute value of r. If I really wanted to be precise about this, I would take the limit from both sides of 0. I would do the limit as r approaches 0 from the right, limit as r approaches 0 from the left. Because technically r can be negative. It's kind of weird when you think of r being negative, but it's totally valid and allowed. So we can say the limit as r approaches 0 from the right. Well, if r is positive, then the absolute value of r is just r. Right? What's the absolute value of 5? Just 5. So then we cancel an r. We get the limit as r goes to 0 of r sine theta cosine theta over r over not r over 1. Sorry, that's terrible. Apologies. And then I would just say this is 0 times whatever cosine of sorry, I got that out of order again. Those are real numbers. 0 times anything is 0. But if you really, well, in fact, we'll do that for the next one. Then we look at the limit from the other side of zero. If you're approaching zero from the left, now the absolute value of r is equal to negative r. Just like the absolute value of -5 is -5. That reduces down to the limit as r goes to 0 from the left of r times sine of theta over times cosine of theta over -1. And then we just get 0 times sine of theta times cosine of theta, which is equal to 0. Technically here, if you really wanted to, like right here, you could have done the thing he did where you say, okay, well, I know that sine of theta is between 1 and -1. I know that cosine of theta is between 1 and -1. You multiply them together, sine theta times cosine theta should also be between 1 and -1. So then, that's interesting. I hadn't thought about that. Cool. Anyway, so then we could say, great. So then r sine theta cosine theta is between r and -r. But if r goes to 0, then the middle thing goes to 0. I don't think you need to do that, but I am not your teacher, so yeah. I also think you could have done this one not using polar coordinates. You can make just a straightforward squeeze theorem argument here. I don't think you could have for the last one, the x cubed plus y cubed over x squared plus y squared one. I don't think there's a squeeze theorem argument for that one. But here, you can totally make the following argument. So check this out for a second. You could say, I know that x, sure. I know that x over the square root of x squared plus y squared is less than or equal to 1. Is it? He says. It is. Here's what I'm thinking of. X is definitely less than or equal to the square root of x squared. And it's also bigger than or equal to the negative square root of x squared. If x was 5, 5 is less than or equal to the square root of 25. If x is -5, -5 is bigger than or equal to the negative square root of -5 squared, which is -5. And then you can say, well, then if I add on a y squared inside here, x is for sure between something that's, in fact, let me do it this way. Sorry. That's definitely less than the square root of x squared plus y squared. And that's certainly bigger than the negative square root of x squared plus y squared. Sorry, I know it's messy. Apologies. So then since x is less than that, we can say that x divided by that is less than or equal to 1. And since x is bigger than that, we say that x divided by that is going to be bigger than or equal to -1. Or as I would prefer to write, the absolute value of x over the square root of x squared plus y squared is less than or equal to 1. And then you take the thing you want to take the limit of, and you fix this to look like that. So check this out. I know it feels weird, right? Like, in fact, maybe do I really want this part here? No, not really. Let's do it this way instead. Let's multiply. Let's forget about that. And let's just multiply everything by y. -y less than or equal to x times y over the square root of x squared plus y squared less than or equal to positive y. And now, as xy approaches 0, 0, where does y go? If xy is approaching 0, 0. Gotta go to 0. Similarly, -y also goes to 0. So the thing in the middle has to get squeezed to 0. There's no other choice. By the squeeze theorem, the limit as xy approaches 0, 0 of x times y over the square root of x squared plus y squared has to be 0. That said, if it gives you a limit and says to use polar coordinates, you should probably just use polar coordinates. But if you see that and you can't make it work, you could try to make a squeeze theorem solution work, and I imagine it'll be worth some partial credit at least. Or you could just say, I'm going to skip that problem and do it last. That might be the best option. If you feel like this problem is out there for you, skip it. Do the ones you know how to do first. In fact, that's just advice you should always take when you're taking a test. If something looks terrible, skip it, come back to it later. Questions about this before we move on to other things? Yes. For where? Sorry. Oh, sure. Because when you take the square root of something squared, it's equal to the opposite. So like, for example, because so if I say the square root of r squared, well, what's the square root of 6 squared? Right. What's the square root of negative 6 squared? Also positive 6. So since we put in something positive, we get something positive. We put in something negative, we get something positive. That's the same as saying, oh, but that's the absolute value of 6. That's the absolute value of negative 6. So taking the square root of something squared is literally the same as taking the absolute value of that something. It keeps it positive as it was, it turns a negative into the corresponding positive, and that's the same function. So that's why we write that the square root of something squared is equal to the absolute value of that something. Cool. All right. So we got 20 minutes left. I feel like we should, I feel like I should talk with words that make sense. I thought we should take a look at that homogeneous problem that we started last time, personally, unless there are other things you would prefer to do. But seeing as how no one's saying anything, I'm just going to do that. So I'll remind you, last time we started this homogeneous problem, and right, there's lots of pieces of this problem. So, I'm sorry. We'll actually answer your question right here too about the autonomous stuff. So, we were given this system here. It is clearly non-homogeneous because we have extra pieces right here. So when you've got a linear system of differential equations like this, where you can write it as a matrix times x1, x2 plus some leftovers here. If those leftovers are anything other than 0, 0, even if there was a t over here, right, that would also be a leftover, right? T is not the x1, x2, but this is definitely non-homogeneous because of the leftovers. It is linear because every variable that's occurring is only multiplied by a constant. Right? There's no x1 squared. There's no x1 times x2, stuff like that. And then finally, this is autonomous because the differential equations only depend on the dependent variables. These differential equations only depend on x1 and x2. If they depended on t as well, then they would be non-autonomous. And if they depended on t only, which is not what we usually encounter in this class, they would also technically be non-autonomous, and we call them pure time, because that's what we call them when it depends on t. So this is definitely autonomous right here. I'm curious, yeah. No, yeah. Whereas just to show you something different, this example here is definitely, I mean, obviously, because it's literally, you're told it is non-linear. You have an x1 times x2, which is making it non-linear. Yeah. Okay. So we rewrote the equation as a matrix equation. So the matrix -8, 5, -7, 4 times x1, x2 plus the leftovers. 2, 1. We did that. We talked about how it's non-homogeneous and autonomous. We found the equilibrium. So here's how we found the equilibrium. Here's how you always find the equilibrium. Set the thing equal to 0 and solve. I skipped that step. I said, well, instead of setting this equal to 0, I'm going to start off by moving this over to the other side of my equal 0 and get this matrix A times X equal to the negative of that, which is -2, 1, or -2, -1. And then to me, it felt like the easiest way to solve this system would be to take this equation A times X equal to B and multiply both sides by the inverse of A. There are other ways of doing it, but honestly, this is probably the fastest way. So if you're trying to solve something like this, and you can find the inverse of A relatively quickly, I think you should do it that way. And again, for a 2x2 matrix, the inverse is not terrible. You're doing 1 over the determinant. That's 1 over -32 minus -35. And then you're taking that matrix and you're interchanging the diagonals and you're changing the signs of the off diagonals. So the -8 and the 4 switch places, and the 5 and the -7 change to -5 and +7. And then you take that inverse, which I simplified as 1/3 times 4 negative 5 7 negative 8, and you multiply it by this vector negative 2 1. We did that, we multiplied it out, we got 4 times negative 2 plus negative 5 times negative 1, and we got 7 times negative 2 plus negative 8 times negative 1, and that ended up being 1/3 times negative 3 comma negative 6, which ended up being negative 1 negative 2. And then since the numbers were nice, I decided I was going to go back and check them real quick just to make sure. So I thought, oh, if I plug in negative 1 for x and negative 2 for x2, up here I'm getting positive 8 minus 10 plus 2, which does equal 0, and positive 7 minus 8 plus 1, which also equals 0, as it should, the solution. Okay, the rest of this is finding the solution like you normally would. So what I would say for a non-homogeneous system like this is after you've done this, found the equilibrium, the rest of it is ignore the non-homogeneous part. Just deal with the matrix A like you usually would. Find the eigenvalues, find the eigenvectors, write the solution in the usual way. So let's do that. So we did that part. Now we're finding the solution. So our matrix A is -8, 5, -7, 4. Also, just a word of advice. It feels like Saito is a pretty well thought out guy. Like he takes the time to make sure the numbers on his exams don't suck. So if you are doing this and you're getting eigenvalues that are crazy, it's probably a good idea to go back and check your work. Make sure you're not missing a minus sign somewhere, because I would be willing to bet the eigenvalues are going to be nice. I guess they could be imaginary. I hope they're not imaginary. That seems really terrible, but he could do that. It's fair game. But based on this, I'm guessing probably not. So let's see. So here's our matrix. So we're going to find the eigenvalues. So lambdas, determinant of -8 minus lambda, 5, -7, 4 minus lambda. And we're going to get -8 minus lambda times 4 minus lambda minus 5 times -7 equal to 0. Simplifying this, we get lambda squared. You always get lambda squared. Can't not get lambda squared. And then you've got -4 lambda plus 8 lambda. It's going to be plus 4 lambda. And then -8 times 4 is -32 plus 35. I should have already known this was going to be a plus 3 over here, though, because I already knew the determinant was positive 3. This is going to end up being lambda squared plus 4 lambda plus 3 equal to 0. And yay, it factors. Lambda plus 3 times lambda plus 1 equal to 0. So we're going to get lambda equal to -1 and lambda equal to -3. And based on that, you should all be able to tell me right now how we would classify our system. Is it a node, a spiral, or a saddle? It's a node because the eigenvalues are real. Is it stable or unstable? Definitely. Cool, good. So that's those are the last two questions. So we've already done the last two questions. Now we just have to figure out the solution. So for lambda equal to 1, okay, I'm gonna do it the way he does it, or the way you all do it. So I'm gonna take my a minus lambda I, so -8 minus -1, 5, -7, 4 minus -1, times my x1, x2 equal to 0, 0. And let's see, rewriting this, it's going to be -8 plus 1 is -7. So you get -7, 5 and -7, 5, which is pretty typical when you do it this way. Like usually the rows either look the same or very easily seem to be multiples of each other. So our equation is -7 x1 plus 5 x2 equal to 0. And if you have the choice, if one thing's negative, one thing's positive, bring the negative thing to the other side to make it positive. So I would write this as 5x2 equal to 7x1. And then my vector is going to, my eigenvector is going to be x1 equal to 5, x2 equal to 7. Cool. Similarly, for lambda equal to -3, let's see even quicker. So I'm going to get -8 minus -3. So -8 plus 3 is -5, 5, -7, and 4 minus -3 is going to be 4 plus 3, which is 7. And so we see we're going to get, again, both of these equations are the same. it's negative 5x1 plus 5x2 equals 0, or negative 7x1 plus 7x2 equals 0. Those are the same equation, just, a little bit different. So negative 5x1 plus 5x2 equals 0. So 5x2 equals 5x1, or x2 equals x1. Our eigenvector is 1, 1. Yeah, you could pick something else, but make the normal choice, the one where the integers are as small as possible, and yeah, don't have any, and you avoid fractions if you can. All right, so then we're gonna write our system. Our solution is gonna be, and I have to remember myself how this works. So our solution is C1e to the lambda 1t times v1 plus C2e to the lambda 2t times v2. And then I think we just tack on the equilibrium solution. That's not right. No, that is right. Sorry. Sorry. It's a little confusing because that's very similar to the leftovers. Like the leftovers were 2, 1, and the equilibrium was -1, -2. So it's easy to get them confused. Yeah. So, check one thing here. I'm just double checking to make sure I'm actually doing it right. Yeah. Cool. Yeah, we're good to go. So the last thing we need to do here is use our initial conditions. Right. Sorry, I'm making sure I'm really not doing something stupid. No, that's right. Okay. Okay. Yeah, that feels right to me. So we're gonna write this in the normal way. X of t is equal to C1 e to the -1 times t times v1, which was 5, 7, plus C2 e to the -3t times v2, which is 1, 1, plus -1, -2. And then we're going to use the initial conditions, which were x1 of 0 equals 3 and x2 of 0 equals 0 to solve for C1 and C2. So we know that if we plug in t equal to 0, x1 equals 3 and x2 equals 0. So we're getting here is 3, 0 equals C1. I don't want to write e to the 0 because we know it's 1. So C1 times 5, 7 plus C2 times e to the 0 times 1, 1 plus -1, -2. And I hope I'm doing this right. I find this part a little, I'm not gonna lie, the non-homogeneous stuff always feels like I have to think just a little bit harder to figure out. So if it were me, I would make some observations here. What would I do here? What is he doing? Sorry, I'm looking at the solutions here. Like, what does he do here? He does do that. Okay. Cool. Yeah, that's totally fine though. Okay. Cool. All right. I'm not doing anything wrong. Great. So I would do exactly what I'm supposed to do. I would add this over to the other side and say 4, 2 is equal to the same thing. Now, again, this is a situation where you can try and solve this in whatever way you like, but the easiest way to solve it, if you don't have any zeros, like if there was a 0 somewhere, you could solve this really easily. I should say, if there was a 0 in one of these eigenvectors, you could solve this really easily. Because if I had a 0 there, I'd be like, oh, well, C2 times 1 has to be 4, and then I can figure out the rest of it really easily. But if there isn't a 0 somewhere, it's not that easy to solve, and it's probably going to be, I don't know. I would probably still do it this way, depending on what here's what I see. So I have 4 equal to 5C1 plus C2. I have 2 equal to 7C1 plus C2. And then the reason I did it this way is because I noticed that the C2 coefficient was going to be the same both times. And so if I subtract these equations, the C2 disappears. That's what I would do in this instance. So subtract 4 minus 2 is 2. 5 minus 7 is -2. C2 minus C2 is 0. You get C1 equal to -1. And then you plug that back into one of these places. And you say 4 equal to 5 times -1 equals C2. Sorry, plus C2. So then add 5, 9 is equal to C2. So then your final solution here is that x of t equals C1 e to the -t times V1 plus C2 e to the negative 3t times v2 plus your equilibrium. And just to double check. Yep, looks right on. Great. That's how I would do a problem like this. One thing I wanted to say before oh gosh, what was the thing I wanted to say? Nope, it's gone. Okay, yeah.
Is there any way you can do that differently, like, for example, doing C?
Yes, that's what I wanted to say. So another way to do this is to say you have 4, 2 equal to the matrix 5, 1, 7, 1 times C1, C2. And then you multiply both sides by the inverse. Is that better? I don't know. It might be better. That's certainly how he does it in the solutions. So then you would say the inverse of this, which is going to be 1 over the determinant, 5 minus 7, times, so then the inverse here is going to be you switch the diagonals, change the signs of the off diagonals, and you're multiplying that matrix by 4, 2 to get C1, C2. It doesn't feel better to me, but it could in a different, right? Maybe if you have grosser numbers over here, it might be easier to do this. So just to show the work, I would do the matrix multiplication first. So I have negative 1/2 times 4 minus 2, negative 28 plus 10. And then negative 1/2 times that is exactly negative 1, positive 9, which are exactly my C1 and C2 values. Yay. Cool. Other questions about this? Yeah,
I was actually wondering if for the 4 equals.
this here.
Yeah, if you could do like C2 equals 5C1 plus 4 and.
But close, except it'd be C2 equal to 4 minus 5C1.
Okay.
But yeah, you could totally do that. If you see one you can easily solve for or isolate, you can totally isolate it and then plug it into the other one. That'll work as well. To me, that always feels like the longest way to do it, but that's me, right? If that's the best way for you to do it, you should do it that way. Maggie.
Okay, not related to this. But
Sure.
With question 5 in the similar format.
Similar, but not the same, because question 5 is non-linear. So they're asking you a little bit different stuff. So let's actually look at question 5 in the last 3 minutes here.
You know, like, oh no.
As a reminder, your exam's on Tuesday. So I'll be in office hours on Monday in drop-in. You also come find me if you're looking for help with questions. So let's look at this one here. Following system of nonlinear differential equations, we have the following. This is number 5. We have dx1 dt equal to ax1 plus x2 minus x1 x2, and dx2 dt equal to 2x2 minus x1 x2. And I'll point out, he says a is a real number and a is not 0. So our stability or instability might depend on whether a is bigger than something or less than something. First, compute the Jacobian. Okay, Jacobian is not a big deal. It's going to be, I usually like to call this f and this g. So the Jacobian is going to be the partial derivative of f with respect to x1, of f with respect to x2, g with respect to x1, g with respect to x2. Which is going to end up being, let's see, so the partial of f with respect to x1 is going to be a minus x2. And then with respect to x2 is going to be 1 minus x1. And then with respect to, for g with respect to x1, it's going to be minus x2. And then for g with respect to x2, it's going to be 2 minus x1. Cool, I like that. Find the x1 null cline and the x2 null cline. Okay, so this is a x1 null cline. You're just setting the x1, the dx1 dt equation equal to 0. You're going to set ax1 plus x2 minus x1 x2 equal to 0. Yes. And then sadly here, we can't factor anything out, which is disappointing. So when you can't factor anything out, then I resort to typically trying to isolate x2, because that's what I'm thinking of as my y, and it just feels better to me. Again, here I don't think it really matters which one you pick, because it's pretty similar either way. So if I try to isolate x2, I'm going to say that ax1 equals x1 times x2 minus x2. And then factoring out an x2 from the right-hand side, x2 times x1 minus 1 is equal to ax1. And then finally, x2 is equal to ax1 divided by x1 minus 1. I don't love this question. Find the null line. Great, there it is. He didn't say graph it, so I'm not going to graph it. Is that what he did? Let's see what he did. I know it's 2 o'clock. Yeah, okay, that's what he did. All right, it seems silly. I don't know why he read it like that. Okay. Anyway, let's find the x2 null line, which is gonna be a little bit nicer. So for me, I would have I don't know. I would just start finding equilibria personally, but you should read the question and do what the question says. So x2 null line, you've got 2x2 minus x1 x2 equal to 0. Factor out the x2, and your null lines are going to be either x2 equal to 0 or x1 equal to 2. I will stress one more final time. 2, 0 is not an equilibrium. You have to have both of these satisfied. So great. Now we can find our equilibrium by, oh, sorry, where's the question here? Yeah. So then the equilibrium. So if I set x2 equal to 0, and then plug it back in over here, I'm going to get ax1 over x1 minus 1 equal to 0, which means x1 has to be 0. There's no other way we can solve this. And typically, not always, but almost always 0, 0 is going to be an equilibrium. So it's a pretty good bet that 0, 0 is going to be an equilibrium. Or if we set x1 equal to 2 and plug that in, then we're going to get that 2 times a over 2 minus 1 is equal to x2. So x2 is 2a. So here's our other equilibrium, 2 comma 2a. And now our job is to classify them. Now I want to point out, when you classify them, notice what he asks you to do. He says, determine if each equilibrium is locally stable, unstable, or inconclusive. He is not asking you to say you have a saddle or a node or a spiral. He just wants you to talk about stability. So let's find the Jacobians and see what we get. And let's do the easier one first. 0, 0 is clearly the that's not true. It might not be the easier one. Let's do it anyway. You have to do both anyway. Again, if you need to leave, you can. We'll wrap this problem up and then we'll call it a day. So J of 0, 0 is going to be A, 1, 0, 2. So based on this, we know the eigenvalues would be what? A and 2. So the eigenvalues would be A and 2. So either A is positive. So if A is positive, okay, what kind of thing would we have if we were allowed to say what kind of thing we had? If I said, do we have a node or a spiral or whatever, if A was positive, we'd have 2 positive eigenvalues, which would mean we would have a node. Specifically, a what kind of node? Right, so if A is positive, unstable. What if A is negative? Be careful. Saddle, which means unstable. So no matter what here, you get instability either way. So no matter what, the equilibrium 0, 0 is always locally unstable. Cool. Now I will point out the other way to do this would have been to have said the trace is equal to a plus 2 and the determinant is equal to 2a minus 0. So, and then if we break it up, right, if a is positive, then the trace is positive, so it's unstable. Doesn't matter, the determinant's also positive, right? If one of the, so to be stable, you need both the trace to be negative and the determinant to be positive. And if one of those things fails, then it's unstable. If A was negative, the trace would be, well, the trace is questionable, but the determinant is negative, which means unstable because it's a saddle. I don't know if this is the best way to do this for this particular problem, but that's the way I'm going back to think. And that's that theorem. whatever from whatever section. I think it was theorem 16, I think, from some section about this. Okay, let's look at the last one real quick here. Again, if you need to go, that's totally fine. The other one was a 2, 2a. So J of 2, 2a. Plugging that in, we're gonna get a minus 2a, comma 1 minus 2, negative 2a. And sorry, no comma there. Don't write commas in your matrix. And then 2 minus 2. So here we're getting the matrix ish. Negative a. Sorry, I'm writing terrible things here. Negative a, negative 1, negative 2a, 0. I don't love this really at all. Yeah. I would probably do the trace determinant way. So the trace is negative a. The determinant is 0 minus that. So the determinant is positive 2a. So it looks like if a is positive, then we have stability because our trace is negative and our determinant is positive. And those are the two things that need to be true. So if a is positive, stable. If a is negative, then we fail hard. So a is negative, both the determinant's negative and the trace is positive. It's unstable.